Now let's work on exercise question 4. Let's read the question first. Customer seeking service arrived at an average rate of 3 per hour with Poisson distribution. So this is talking about arrival rate. Average rate is 3 customer per hour. The next sentence says the average time to install a muffler is 15 minutes with exponential distribution. So some people may wonder, what is 15 minutes? Is this service rate or is this service time? So this is 15 minutes. So of course, this is service time. So typically when we talk about service rate, it's how many customers you can serve per hour. It's called service rate per hour. Number of customers per hour is called service rate. But 15 minutes alone, this is service time. So basically means we may have to convert 15 minutes to the corresponding service rate. So now we know the first piece of information, which is arrival rate, 3 per hour. We know the service time, which is 15 minutes. We need to figure out what is service rate. So arrival rate, lambda is 3 customers per hour. Service rate, mu, is equal to 60 minutes divided by 15 minutes to serve each customer. So 60 divided by 15, we have 4 customers per hour. So this is service rate. This is a mu. So then we also can calculate rho. Rho is lambda divided by mu, which is 3 divided by 4. We got 0.75. Now let's try to solve the first question. So on arrival at the garage, how many customers should one expect to find in the system? So how many customers in the system? The number of customers in the system. So if you rethink about the formulas we covered in the beginning, this is really talking about the number of customers in the system, which basically means LS. So LS, the question is asking about what is LS, given lambda, given mu, what is LS? So if you look at the formula, LS is equal to lambda divided by mu minus lambda. So we're plugging all the numbers, we'll get 3. So average-wise, one should expect to find 3 customers in the system. So now we have the answer for question 1. Now let's look at question 2. The management is interested in adding another mechanic when the customer's average time in the system exceeds 75 minutes. If business continues to increase, at what arrival rate per hour will additional mechanic be needed? So this is a little bit unusual question. So here, the question asks about at what arrival rate. So basically the question asks about the lambda. So what should be the lambda? So lambda now is unknown. What is known? The known information is when the customer's average time in the system exceeds 75 minutes. So average time in the system is known and arrival rate is unknown. So that is the question. So what is the average time in the system? So average time in the system is WS. So this is the formula. So WS is equal to 1 divided by mu minus lambda. So if you look at this equation, for this particular question, WS is a known number. It's a given information. And mu is also given information. Lambda is unknown. So given WS, given mu, we don't know lambda, so we need to figure out what is lambda. So we plug in the value for WS and as well as mu, that we can solve for lambda. So if you look at it here, so mu is equal to 4, WS is 75 minutes. 75 minutes. So shall we just use 75 minutes here? So be careful, because for both mu and lambda, we use the rates per hour. So to be consistent, WS, we have to use hours. So we cannot use 75 minutes. We have to convert 75 minutes to how many hours? So we use 75 divided by 60. So that is that equation. Okay, this is the equation. So 75 divided by 60, we get 1.25. So basically 1 divided by 4 minus lambda equal to 1.25. So you can solve this equation, you will get lambda equal to 3.2 per hour. So this is the answer. So basically at the rate when the business continue to grow and at this arrival rate, 3.2 customers per hour, then we may have to consider adding another mechanic, because then the customer's average time in the system will exceed 75 minutes. So that's how I'll solve it. So question 2 is a little bit unusual. Now let's look at exercise question 5. Let's read the background information. The arrival rate averaged 6 boats per hour, Poisson disputed. So of course, 6 boats per hour. It looks like this is the arrival rate, 6 boats per hour. The average time to launch or retrieve a boat is 6 minutes. So this is a service time. It takes 6 minutes to launch or retrieve one boat. With exponential distribution, assume that only one boat can be launched or retrieved at one time. So we have the arrival rate. We also have the service time. We need to figure out what is that service rate. So read question 1. The LCRA plans to add another ramp when the average turnaround time. So what is average turnaround time? Average turnaround time is the average time in the system. So which is a WS. So when WS exceeds 75 minutes, at what arrival rate per hour should the LCRA begin to consider adding another ramp? So this is similar to question 2 in exercise problem 4, the one we just covered on the previous slide. So first of all, if you read the question, we know lambda, based on the background information, lambda is equal to 6 custom per hour. Mu, if you do a little bit conversion, it's 60 divided by 6 minutes per boat. 60 divided by 6, you have 10 per hour. So this is the current service rate. This is the current arrival rate. So we can calculate rho. Rho is lambda divided by mu, which is 6 divided by 10. We have a 0.6. So now let's try to answer question 1. So question 1 is a little bit unusual. So for question 1, what we want to solve is the arrival rate. Okay, so don't look at this one. We're looking at a new rate. So what should be the arrival rate? So arrival rate, lambda is unknown. So what is known information? The average turnaround time. In other words, the average time in the system, which is at WS. So WS is known. Arrival rate, lambda, is unknown. So we have to solve it. So look at that formula. The formula WS equal to 1 divided by mu minus lambda. So if you look at this equation, I have 3 numbers, WS, mu, and the lambda. So first of all, which number is unknown? Lambda. This is the number we try to solve. At what arrival rate? So lambda is unknown. So what about mu? Mu will be 10 per hour. What about WS? WS is the average time in the system, so which is given in question 1, which is 75 minutes. Again, because 75 minutes, we have to be consistent. If you look at mu and lambda, both are the rate per hour. So we have to convert 75 minutes to how many hours, just to be consistent. So we don't use 75 here. Instead, we use 75 divided by 60. We try to convert minutes to hours. So once we have this equation, you can see once you plug in the value for WS and mu, the only unknown number is lambda. So we can solve this equation. If you solve it, you get lambda equal to 9.2. So currently lambda is 6 per hour. We don't have any issues. So it's not a problem. But if lambda continue to grow, once lambda reaches to this level, 9.2 per hour, then we may need to add another ramp. So that's how we solve the question. So let's look at question 2. If there were room to park only 3 boats at the top of the ramp in preparation for launching, how often, or in other words, how likely, would an arrival find insufficient parking space? So if you look at the question asks you the probability. How likely, how often, how likely. It's talking about probability. So if you go back thinking about the 3 type of formulas we discussed, so the 3 types, one is about, the first type of problem is about probability. So this question is talking about probability. So how often or how likely? So how often or how likely would a rival find insufficient parking space? So when do you find insufficient parking space? Currently, there are only enough space to park 3 boats. So when do you find insufficient parking space? When there are 4 or more boats in a system. That means we don't have sufficient space for all the boats because we'll only allow 3 boats. So currently, we only have enough space to park 3 boats. So when you have 4 or more boats, then there's not enough parking space. So basically, the question talking about how likely, what's the likelihood that there will be 4 or more customers in the system? So how likely there will be 4 or more customers in the system? So if you go back, look at the formula. So which basically is the probability that there are at least 4 or more customers in the system. The formula will be rho to the 4th power. Then rho is equal to 0.6. 0.6, then we do the math, you get 0.1296. So basically, this is a probability. It's close to 13%, 12%, 12.96% time an arrival will find insufficient parking space.